Welcome to Study Time, a televised home learning program produced by Rwanda Education Board.
Hello students, I hope you guys are doing well and you are glued to your TVs for our nice programs where we can learn lots of subjects. As always, today I am your teacher for physics and my name is John Bosco. The short form is JB. So I am welcoming you to this lesson because we are going to be learning very interesting things, interesting concepts in physics of Senior 2. And the unit we are still looking at is Unit 4, which is about density and pressure in solids and fluids. And today's lesson is going to be based on pressure in fluids and then atmospheric pressure. So we are going to continue from what we were looking at last time. So the main objective of our lesson today, that means at the end of the lesson, you as a student, you must have understood the connection between pressure in fluids and depth. That pressure in a fluid depends on depth. And how? You see? Then two, we must also be able to understand at least the basic definition of atmospheric pressure. That is what we are going to look at today. Pressure and depth and atmospheric pressure. And so, to start with, we want to look at the experiment to show that pressure in fluids increases with depth. If you remember, what we said last time was that if you have a liquid like this, I hope you can see this very well. This is water in a measuring cylinder. If we are measuring depth, the upper meniscus of this water is here, the upper level. If you are measuring depth, we begin from here as we go down. That's what we call depth. So if I move from here and I go there, this becomes my depth. And I can measure that depth using a meter rule. So we want to see the relationship between pressure in a liquid like water and depth. And this is the experiment that we are going to demonstrate here in class. We are going to do here in class. But remember, you can do this at home. And as I told you, we really want to make physics very simple. We don't want to complicate it because it has never been complicated. So what I've done here is I've got a mineral water bottle, which you can afford, I'm very sure. And I have created holes at the side using a pin, small pin that you can afford. So this is the first hole, second, third, which is pretty much the same as this. A, B, C. I hope you see that. You can do this at home. And I have closed the holes with a piece of clay. If you don't have clay or plasticine, you can use soap. Just soak it in water, become soft, then you can use it. So I'm going to fill them up with water. I'm going to fill up this bottle with water. So I'll get my funnel and then fill it up with water. Funnel is quite small. The outlet is small. That's why water poured out. So let me try to do it quickly. I'm going to add more water until the bottle is full. Keep thinking about the questions that have been asked. You can see the questions there, because once I open the hole, water will then jet out. That means water will come out. So we want to find out from which hole will water come out fastest and from which hole water will come out slowest. And also why. Those are the things, the questions that we want to answer at the end of this. And so I have already filled up the bottle with water. So the next step, as you observe very carefully, I'm going to open the holes by removing this soap, removing this, and then removing this soap. I'm removing them carefully. Look at how water is jetting out from these three holes. This is hole A, this is hole B, and this is hole C. The speed at which water is coming out from hole B is not the same as the speed at which water is coming out from hole A. And it's not the same as the speed at which water was coming out from hole C. All different, as you can see. The water from hole B is landing so close to the bottle. The water from hole A is going very far. So let us look at the questions that have been asked here. One, they are saying, water jets out fastest from which hole? Remember, here we have three holes. We have the lowest hole, which is A, and then this in the middle, which is B, and the uppermost, which is C. So water jets out of hole A at the fastest speed, as you can see, what we saw in that experiment. So it means here we are going to write A. Water jets out at the fastest speed from hole A. Then, water creates the deepest hole in the sand. If we allowed our water to fall on the sand, it would create a hole on the sand. So which of these three holes do you think would create the deepest hole in the sand? Is it from water coming from C, or water coming from B, or water coming from A? What do you think? Great. As we have seen, because water is coming out fastest from hole A, the water from A will be moving with the greatest speed and the greatest force. So this hole will be the deepest hole, followed by the one coming from B, and then lastly, the one coming from C. So it means here the deepest hole will be created by water coming from hole A. Then, water jets out slowest from which hole? Again, from the experiment, we have seen that water will jet out slowest from the uppermost hole, which is hole C. So it means here our answer is what? Our answer is C. So from this experiment, what conclusion can we make? Try to draw a conclusion between liquid pressure and depth. What conclusion can we make? Well, the conclusion we can make, I think you have made it correctly also, is that pressure in a fluid like water or any other liquid increases with depth. So that means the deeper you go inside the liquid, the higher the pressure. If you're on the liquid surface, right on top, you have less pressure. As you go inside the liquid, then you are going to experience a higher amount of pressure. And that is what this experiment is dealing with. So the conclusion from that experiment is that pressure in fluids increases with what? With depth. Pressure in fluids increases with depth. Remember, when you talk about depth, we begin measuring the depth from the top of the liquid, from here as we go down. That is our depth. Now, before we look at the applications of this content, of this concept, let us go back to the previous homework. Do you guys remember the homework that we did last time in the last video, in the last lesson that we had? It was a question that was asking us to find pressures in the water, in the liquid at different points. This was the question. I'm not going to go through all the parts of the question. I'm going to look at only two, because there are two major aspects in this question. So I am going to calculate, because we are told to calculate pressure at A, at B, at C, F, and all this, and then pressure difference. So I'm going to calculate pressure at A to check your answer, and also pressure at B Then I will answer the first part there, just to compare your answer. So let's move. What is the liquid pressure at point A? Look at this. The liquid stops here. Is there any liquid at point A? No, it is air. And here we are assuming the atmospheric pressure is 0. Right. Remember, our previous homework was asking us to calculate pressure at different points in a liquid. So I am going to answer only pressure at A, just to check your answer, pressure at B. Then we also look at pressure difference between B and D. Those are the areas I'm going to look at. Otherwise, the rest are very similar to those two concepts. So beginning with pressure at A, remember A is above the liquid, and we have not entered inside the liquid. So that means H is 0. So from the formula, pressure is rho GH. Our rho, which is density, is 800 times G, which is 10, and H, which is what? 0. So if you multiply anything by 0, you can see we have 0 Pascal. So the pressure at A is 0. Then going to B, pressure at B. B is on the surface of the liquid. We have not yet entered the liquid. Remember we said when you're measuring the depth, we begin from the bottom as we go down. So the pressure is rho GH, which is going to be 800 times 10. Let's look at H. At point B, it is on the surface of the liquid. We have not gone inside. So it means H is also going to be 0. When you multiply that, we come out with 0 Pascal. So the pressure on the liquid surface is the same as the pressure above the liquid surface if we ignore the atmospheric pressure. Now let's look at B, Roman 1. Roman 1, we want to get the pressure difference between B and D. Pressure at B, we have already found out. Pressure at B, remember, B is this point on the surface. Pressure at B is 0 Pascal. Now we want to look at pressure at point D. So let's check the pressure at point D. The pressure at point D will measure the depth beginning from the liquid surface. So this is 30 centimeters and this is 20 centimeters. So it means this depth here from 20 to 30 is 30 minus 20. And 30 minus 20, we come out with 10. So pressure is rho GH. That gives you 800 times G, which is 10, times H, which is 30 minus 20. And 30 minus 20, what do you get? We come out with 10. Remember, this is 10 centimeters, so we need to divide it by 100 so that we can change it into meters. So if we simplify this, we are going to come out with 800. And the SI unit of pressure is Pascal. So that means the pressure is 800 Pascal. So pressure difference, because that is what is asked, pressure difference is going to be, as we saw in the previous experiment, the pressure at D is greater than the pressure at what? At B. Because D is inside the liquid. You say as you go deeper inside the liquid, then the pressure increases. So this is going to give us pressure at D minus pressure at B, which is going to be 800 minus what? Minus 0. 800 minus 0, we are going to come out with 800 Pascal. So it means the pressure difference between B and D is going to be 800 Pascal. Great. So I want you to check the rest of your working, just in case you made some mistakes, and correct them. We also get the pressure difference between B and G. If you look at B, B is right here on top, and G is there. Pressure at G should be more than pressure at B. Then you can find the pressure difference. So that is a direct application of the experiment that we just looked at previously. So the next item is going to be applications of pressure in liquids in everyday life. This experiment that we saw here, pressure increasing with depth, has got so many applications. One, the wall of a dam, like in a reservoir, is built in such a way that the walls are very thick at the bottom, as this diagram illustrates. It is thicker at the bottom, and it is thinner on top. Thicker at the bottom because the liquid pressure at this point here, the liquid pressure here is very high, and the liquid pressure there is low. So you make this thick so as to withstand the liquid pressure. Otherwise, if you make it is built of the same thickness, then the dam will collapse due to the pressure being exerted by the what? By the weight of the water. Two, deep sea divers, these are people who dive, they enter deep into the sea, sometimes to do some studies in the sea. They wear special suits which are made of reinforced aluminum so as to withstand the extreme pressure found at the bottom of the sea, because the sea can be so deep. A sea can be even 50 meters deep, 80 meters deep. You can imagine what pressure will be found at the bottom. Another idea, which is very common, I believe if you look at your surrounding, the houses around, the homes around, you will find people have got water tanks. So water tanks are placed on raised platforms, very high above the house, so that when water is released from this tank, as it comes to your house, it comes with a lot of pressure. Because we have said pressure increases with what? With depth. So when you release water from the tank, which is up there, by the time it reaches your tap in the house, the water will be having a high pressure. And then the fourth one, which they are not the only ones, but we are looking at only 4. If accidentally you cut your finger. Have you ever cut your finger before? Me, I have. Several times, accidentally. So if you cut your finger and you begin bleeding, you don't want to bleed. You don't want to lose a lot of blood. So what do? If you keep your hand lowered like this, remember your heart is here. The heart is pumping blood. So this part of your hand will be having a very high blood pressure. It will have a very high blood pressure. So the best we can do is to raise your finger up, the part which you have cut. When you raise it up, then you are decreasing the what? The pressure. And in that case, you reduce the bleeding. So those are 4 applications of pressure in liquids. But remember, as I told you, they are not the only applications of pressure in liquids. Then the next idea that we want to look at is atmospheric pressure. Remember, all of us on Earth, we are like at the bottom of a sea of gases in the atmosphere. If this is the Earth, the atmosphere is here, surrounding the Earth. So you and me, we are found here on the Earth's surface. So it appears like we are actually carrying the weight of all the gases in the atmosphere. And the weight of all the gases in the atmosphere will exert a pressure on our bodies. And that pressure is called what? Atmospheric pressure. So what is atmospheric pressure? Atmospheric pressure is the pressure exerted by the weight of the gases in the what? In the atmosphere. That is what we call atmospheric pressure. It is the pressure exerted by the weight of the gases in the atmosphere. Now, do you feel this atmospheric pressure? No. Personally, I don't feel it. But it is there. We don't feel it because the way our bodies are made, we have fluids in our bodies like blood that is also flowing, and so many other body tissues which exert a pressure that counterbalances atmospheric pressure. So we don't feel it, but it is a lot. And at sea level, the standard atmospheric pressure is about 100,000 newtons per meter squared. Can you imagine? If you have an area of 1 meter squared, you have learned that before, the pressure that is going to produce on such an area is 100,000 newtons per meter squared. So every meter squared has got a force of 100,000. That is how powerful the atmosphere is. So later on, we shall look at how to measure atmospheric pressure and how we come out with this value. But for now, we want to perform some demonstration to show you atmospheric pressure, existence of atmospheric pressure. And one of the demonstrations that we are going to have is quite very easy. You can perform at home. You get a bottle. Here I have a conical flask. I'm going to try to fill it up with the water. This is water. I just colored it so that you are able to observe it well. So I'm going to add some more water until it is full. Right there, it is full. Then you get a paper, an ordinary paper. Then we place the paper on top of the flask, on the mouth of the flask. That's what I've done. Then using one finger, put it above and turn it upside down. Remove your hand. You see what happens? Does the water pour out? No. Isn't it magical? Me, I find it very interesting. I find it magical. Water does not pour out. If you have time, you can do that with this bottle. You can do it with a test tube. You can do it with a mineral water bottle. It will work. So why is it that this water was not able to pour down? It is because of atmospheric pressure. Atmospheric pressure is countering the weight of the water, pushing the weight of and the paper upward so that the the water does not pour. Secondly, which is our last demonstration for today on atmospheric pressure, and certainly in our next lesson, we shall be looking at atmospheric pressure in details. We want to look at this wonderful demonstration as well. Look at this. Here we got a bottle, could use a mineral water bottle, and a balloon. Do you guys know a balloon? Just open the mouth of the balloon, push the balloon inside, and make sure it is tight on the mouth like I have done. Now, focus carefully on this balloon. It is open, you see? It is open. So it means the pressure inside that balloon is the same as the pressure outside the balloon, which is atmospheric pressure. So what I'm going to do, I'm going to squeeze this bottle. I want you to observe, focus on the balloon and see what happens. So I'm going to squeeze the bottle. Do you see what is happening to the balloon? Okay, let's repeat it. Focus on the balloon and observe what is happening to the balloon. The balloon is becoming smaller. Now, what is the reason? The reason is, as I compress this bottle, the air inside the bottle becomes smaller in volume. When the air becomes smaller, then the pressure of the air inside increases. And when the pressure of the air increases, the pressure of the air inside the balloon does not increase because this is atmospheric pressure, same as the pressure outside. So if I continue pressing the balloon, the balloon will become smaller and smaller because the gas pressure inside the bottle is more than the atmospheric pressure. And if I continue further, this balloon will be ejected out of the bottle. It will pop out. So let us see. Focus on this very carefully and observe what happens. Do you see the balloon becoming smaller? I am going to increase the pressure. Look at what happens. The balloon pops out, and this bottle is able to inflate the balloon. You can do it with this one as well. If I compress the bottle, you see what is happening? The balloon is becoming smaller. If I press it further, the balloon pops out, and then it inflates the balloon. That is an experiment that demonstrates to us the existence of atmospheric pressure. In our next lesson, which is going to be measuring atmospheric pressure, we shall give and look at more explanations on that. So to summarize our lesson, every one of you must have understood that pressure in liquids depends on what? On depth. 2, you now know the basic idea, the definition of atmospheric pressure. I'm going to leave you with this homework that you can discuss at home, and make sure next time when we meet you have the answers ready. Define the term pressure and state its SI unit. That is right from the beginning of Unit 4. What is atmosphere? What is atmospheric pressure? The value of atmospheric pressure at sea level is about 100,000 Pascal. This means that the atmospheric pressure exerts a pressure of, so we need the value of the force. So the atmospheric pressure exerts a force of how many newtons on an area of how many meters squared. Right from our lesson, you should be able to pick that. And this is the experiment that we have done with the bottle. And so read it carefully and see whether you can answer that. And lastly, idea of pressure in liquids is very useful. We can link it to so many subjects, and it's applied in so many areas. For instance, in geography, we apply pressure to discover the direction in which winds flow. You know that wind is moving air. When air begins to move, it is because of pressure difference. So if pressure at point A is high and pressure at point B is low, then wind will move from a place of high pressure to that of low pressure. So as air begins to flow, then we have wind. And wind can lead to formation of rainfall. So that's how useful this topic is. It is useful in even so many other areas that we cannot exhaust right now. And so once again, I want to thank you guys so much for being good students, listening students, and I hope you're going to practice this physics and make physics very interesting. I hope you'll join us next time as we meet for the next lesson. Bye-bye.